Hi everyone, welcome back to Power Electronics session 10. Now we are going to discuss about inverters. But remember, in case of inverters and DC to DC converters, we need two extra circuits to operate the thyristors. One is gate drive or gate circuit to turn on the thyristor. Second one is commutation circuit to turn on the conducting thyristor. Okay, so in case of rectifiers and all, we didn't discuss extra circuit like the commutation because natural commutation is possible. But here, in case of inverters and DC to DC converters, we will have like a DC source. So when DC source is there, natural commutation is not possible. That is what we require extra circuit to turn on the conducting thyristor. But now, in these two circuits, nothing but DC to DC converters and inverters, we require the forced commutation, but we will not show that commutation circuit. We will assume that whenever you want to turn off the conducting thyristor, we will use any one of the forced commutation method, either voltage commutation or current commutation. We are not going to show those circuits. Okay, so that's what I am telling you here. Now, coming back to the actual thing here, that's nothing but inverters. What exactly the meaning of inverter? Inverter is nothing but it's inverters converts the fixed DC. Okay, inverter converts or inverters convert fixed DC to variable AC. Variable AC in the sense, what is the meaning of variable AC? Variable AC means variable voltage or current and variable frequency. Okay, so what is the meaning of that? Either we will vary the output voltage or current based on the type of inverter, and also we can vary the frequency. That's the meaning of variable AC. Okay, now, so what type of inverters we have basically? There are two types of inverters. One is called VSI, another one is called CSI. What's the meaning of these two? VSI means voltage source inverters, CSI means current source inverters. But what's the difference between these two? So voltage source inverter is nothing but it will have a constant DC voltage as a source. And here constant DC, it is also called as a voltage step inverter. So constant DC voltage as a source. And next one is load voltage is independent of type and magnitude of the load. That means output voltage of the VSI will be the same irrespective of the load. Okay, irrespective of the load it will be same. And load current is depending on the type of the load which is connected to the inverter. And this is generally used for low and medium power applications. That's the meaning of VSI. But in our syllabus, we are going to discuss about the VSI meaning. We are not going to discuss about the much CSI. Okay, not going to discuss. Next, CSI. But what is the meaning of the CSI? As I told that current source inverters. But what is the difference between CS and VSI? These are the things. It's almost same as that one, but a little different. It's nothing but like you can say dual property. Okay, dual property. What's the dual property? There we actually given as a constant DC voltage as a source, but we are constant DC current as a source. That means source current is constant. Load current is independent of the type and magnitude of the load. Then load voltage depends on the type of the load. It is opposite to the previous things. Generally used for high power loads. Okay, this is the meaning of CSI. Now onwards, our concentration is mainly on VSI. Okay, so further, what are the different type of VSI circuits? There are two type of maybe you can say these voltage source inverters can be classified into two groups based on the number of output phases. So based on that, it is it is mainly single phase VSI, single phase VSI, then three phase VSI. Okay, so like that. But further, these can be classified into two different groups. That means single phase VSI will have two circuits. One is half bridge inverter, that's the half bridge VSI, and then full bridge VSI. In case of three-phase system, we have two different circuits. That's nothing but 180-degree mode VSI, 120-degree mode VSI. So same classification can be taken in a different way. Nothing but single leg inverters, that's nothing but half-bridge inverter, single phase half-bridge inverter. Single phase full-bridge inverter will be called as two-leg inverters. Three-phase rectifiers, both 180-degree mode and 120-degree mode will be called as three-leg inverters. That's nothing but number of legs we have. Okay, so that's the basic. So now we will discuss about the single phase VSI. Okay, single phase half-bridge VSI in this case. So single phase half-bridge VSI is actually called as like one leg inverter. That's why here we'll have only one leg of thyristors. And here to have this single phase half-bridge VSI, we require 3-terminal DC source. 3-terminal DC source means like this. Okay, so this is the one terminal, the middle terminal is also required, and other terminal. Okay, so this is generally taken as a ground. So now here we will connect the load. Okay, and here thyristors will be there like this. One thyristor will be like this, and other thyristor will be like this. Assume like if you take the kind of like a technology, this is VDC by 2 and this is other VDC by 2. It means totally we are giving the source voltage of VDC. Okay. Then here thyristor T1 and this is thyristor T2. So this is a load. Okay, and we are taking that load kind of like polarity and direction of current. Load polarity, this is negative, this is positive. That means V0. And load current, positive direction of current will be like this. Okay, so that's a mean. So right now you can see that most of the times we may not have the kind of like 3-terminal DC source. In that case, what we need to do, you can take the normal DC source and we can make this 3-terminal DC source with a capacitor potential divider. Two capacitors will be connected across the DC source like this. Okay. So this will make us, because if you are giving VDC, then these two capacitors are connected in series, means it will be voltage will be divided across that. So then what will happen? You will have VDC by 2 and this will be VDC by 2. So you can take this one as a third point. So that means to make the 2-terminal DC voltage to 3-terminal DC voltage, we require an additional circuitry like this. Okay, now look at the circuit diagram now. In this circuit diagram, thyristor T1 and T2 are always forward biased to the source. So that's why you can see that any time we can turn on these two thyristors. Now, to get the output voltage as AC, that means proper AC, if we want to have the proper AC means we need to have the like average output voltage must be 0. That means positive half cycle and negative half cycle exactly same. To get this one, if you assume that output time period is T, that means output time period is T seconds, to get the proper AC current, we will turn on the, we will operate the thyristor T1 for half of this time, T by 2 seconds, and thyristor T2 will also be operated for rest of the T by 2 seconds. That means we will get the exact positive half cycle and negative half cycle. That means to get the proper AC, we need to operate these thyristors for same conduction, but not at the same time. Same conduction means both will be in conduction for the same time, but not together. If both are together in conduction means it source will be short circuited. That's the problem for the thyristors. We will not operate like that. Okay. Here what exactly meaning is you are going to get the symmetrical AC waveform. To get the symmetrical AC waveform, we need to operate these thyristors for the same conduction period. That's the meaning of that. Okay. Good. But another thing, as we discussed in the beginning of the power electronics, in any circuit, in any power electron circuit, you will never ever get the expected AC waveform as it is. What is the meaning of that? Let me explain. Here, inverters means we are expecting the AC as the output. AC means generally what type of waveform we will expect? Proper sinusoidal waveform. But in case of inverters, without using any extra circuit, nothing but any filter, we will get square waveform as a output. Square waveform. But it is AC. Okay. So, but what is the interpretation of the square waveform in general? We discussed already in the case of rectifiers. Square waveform is nothing but it's a sinusoidal waveform only, but it is distorted. That means if you combine a lot of AC sinusoidal waveforms together, that's nothing but like a kind of harmonics are combined, you will get the perfect square wave. So here also in AC, like in rectifiers, in inverters, we are going to get the square waveform as the output, but if you want to get the sine waveform means we need to remove all unwanted components. Those are nothing but harmonics. So if you use the filter at the output and filter out all these harmonics, you are going to get the proper sine wave. So that's the meaning of it. Okay. So these are the things sufficient to start the operation of this inverter. Okay. Okay. So this is a circuit we consider. So now T1 is actually forward biased and we can terminate this thyristor by using any triggering method. Generally we will use the gate triggering. If this thyristor is turned on means it will act as a short circuit. Okay. If it is acting as a short circuit, then what is the equivalent circuit of that? You can take the equivalent circuit as it is like this. So it will be like this. Because this is open circuit means almost it is acting as an open circuit, like almost the circuit can be negligible. That means this voltage will be appear across the resistance. Assume load is resistance here. And this will be taken as a positive here, this will be taken as a negative. That is what we are taking load voltage. This one. And this thyristor is acting as a short circuit and it will allow the current always like this. Now look at that. When you consider this thyristor T1 is turned on, you can see that output voltage polarity positive is connected to positive of the source. Then obviously you will get the positive voltage across the load. And how much voltage we are getting? VDC by 2. So that's what we are getting. And now the current direction. What's the current is flowing through that? Here load will get the current from the source. So this will be the kind of direction of the current. It is supplied by the source flowing through the thyristor and flowing through the load like this. Now look at that. We assume the load current is positive like this. So that means now both are in the same direction. That means when T1 is in conduction, okay, T1 is in conduction, output voltage will be positive VDC by 2 and load. Okay, so load current I0 will be positive. So this is what you need to take it. Okay, so that's now this T1 will be there in conduction as we discussed for T by 2 seconds. That means this will be in conduction for T by 2 seconds. Okay, we will discuss for the other thing, nothing but T2. So now at the end of T by 2 seconds, we will turn on the thyristor T1 and immediately we will turn on the thyristor T2. So that means if you turn on thyristor turn off the thyristor T1 at end of T by 2 seconds, that means using the any post commutation method, and immediately we are actually turning on the thyristor T2, that means it will act as a short circuit. Okay, so that's all. So in this case, what's the equivalent circuit? Equivalent circuit will be like this. So equivalent circuit will be like this means in this case, so source is connected to the load through thyristor T2. T2 is actually connected like this, and it is acting as a, it's like a short circuit, and this is connected downwards, that's why it will allow the current action like this. Now this is the source voltage connected to the load like this, VDC by 2. Okay, and we assume that this is the polarity of the load voltage V0. Now look at here, negative terminal of the source is connected to the positive terminal of the load, that means voltage across the load now it is minus VDC by 2. And what will be the direction of current? As we discussed, current is actually supplied by the source now, and then that is flowing through the load like this. And this, okay, this thyristor will allow the current in the downward direction. That's the current, okay, correct one. So, but we assumed that load current is actually positive in this way. That means load current is positive in this way. But now the current is actually flowing in opposite direction. This is one. So now the current is actually flowing. The load is nothing but reverse to the assumed direction, but negative load current is there. So now when thyristor T2 is in conduction, these are the output voltage and currents. So that means output voltage will be minus VDC by 2 and current will be negative. Okay, so current will be negative. So this will be there in conduction for the rest of the time, nothing T by 2 seconds, for one time period. Similarly, at the end of T by 2 seconds, we will turn off the conducting thyristor T2 by using the postal commutation, and immediately we will turn on the thyristor T1, and so on it will be repeated. That means same things will be repeated. If you take the output voltage and current waveform based on these things, it will be like this. Okay, so for first half of the cycle, we will take the thyristor T1 is in conduction, that means output voltage will be VDC by 2. And here the load is resistive, that's why load current and load voltage will be in the same phase. Same phase is nothing but whatever the current voltage waveform is there, current waveform will also be similar. That means it will also be constant. This will be there for T by 2 seconds. At the end of T by 2 seconds, what we will do? We will turn on the conducting thyristor using the post commutation method, and then this voltage will be coming to 0. And immediately we will turn on the other thyristor. If you turn on the other thyristor T2, then voltage across the load, as we discussed, will be negative voltage. So this will be there for rest of the T by 2 seconds. That means this will be minus VDC by 2. And load is load is resistive load. That's why load current will be exactly in phase with the load voltage. Okay, that means load is resistive load, and in that case resistance can allow the sudden change in voltage and current. So sudden change can be happening. Now at the end of T by 2 seconds, we will turn off the conducting thyristor T2. That means output voltage will be becoming 0, and then immediately we will turn on the thyristor T1, then output voltage will be again VDC by 2, positive VDC by 2. And then again we will turn on the conducting thyristor T1, and then we will turn on the thyristor T2, then it will be minus VD. So, and so on, it will be keep on changing. And load current will be in phase with this, means same waveform will be there but with reduced magnitude. Okay. So this is the waveform. So now here this will be there for t by 2 seconds. And this is there for rest of the t by 2 seconds. That means this is a one complete cycle t. Okay, and if you look at that, means here same waveform. This is by thyristor T1, this is by thyristor T2, again this will be thyristor 1, thyristor 2, and so on. Okay, with this I am stopping here. We will discuss the rest of the loads in the coming video. Okay, so again, I forgot to represent, this is V0 and this is I0. Okay, thank you. We'll see you in the next video.